Welcome back. In this video, we are going to look at example problems of calculating the area of surfaces of revolution. Let's get to it. All right, so here's our first example. We want to find the area of the surface formed by revolving the graph of y equals x divided by 2 for 0 less than or equal to x less than or equal to 6 about the x-axis. And so the first thing that we want to do here is draw a graph of this function. And so I'll start by drawing the y-axis, and then I'll draw the x-axis, and then I'll label them. So this is the y-axis, and here's the x-axis. And then this line, y equals x divided by 2, that would be the same as y equals 1/2 times x. And so that's just going to be a line that crosses through the origin with a slope of 1/2. And so if this is y equals 1, and this is x equals 2, then our line will look something like this. All right, so this is the line y equals 1/2 times x. Or you could write y equals x divided by 2. It doesn't matter, they're the same thing. And so then we're looking at the particular portion of this line from x equals 0 to x equals 6. And so this would be x equals 0. And then if this is x equals 2, then we have x equals 3, 4, 5, 6. And so I'll draw a line there, label that with 6, which means the point on our line at x equals 6 will be right here. And so between those 2 points will be this line right here, which is the line that we are going to be revolving around the x-axis to form a surface of revolution, right? We want to find the area of a surface formed by revolving the graph of that function, y equals 1/2 times x, from x equals 0 to x equals 6, about the x-axis. And so I'm just going to label that. I'll draw an arrow around the x-axis so we remember what axis we are revolving around. Okay? And so if we were to revolve this line around the x-axis, our surface of revolution would look something like this. It's going to create the shape of the shell of a cone. And so in order to calculate the area of this surface, we will need to use the following formula. The area of the surface is equal to 2 pi times the integral from a to b, which are 2 values of x, of the radius in terms of x, times the square root of 1 plus f prime of x squared times dx. All right, and so let's start setting up this definite integral. Let's start by determining our bounds of integration, a and b. Those are the values of x for which the line or the curve that we're revolving around the x-axis lies between. And in this case, that's between x equals 0 and x equals 6. And so we'll start by writing that the area of the surface is equal to 2 pi times the integral from 0 to 6, and then now we need to determine the radius in terms of x. And the radius of our surface of revolution will be the distance from the axis of revolution, which is the x-axis, to our line. And so this distance right here is the radius in terms of x, which in this case is just going to be equal to this line, y equals 1/2 times x. Right, this line is the distance from the x-axis, or the axis of revolution, to the outside of our surface of revolution. And so r of x is equal to 1/2 times x, which we can then plug in for our definite integral, and we'll have 1/2 times x times the square root of 1 plus f prime of x. And f prime of x is the derivative of the function where our line comes from that we're revolving around the x-axis. And so in this case, that is y equals 1/2 times x. And so if we say that y is equal to f of x, then that means that f of x will be equal to 1/2 times x. And so then we could find f prime of x by taking the derivative of 1/2 times x. And so f prime of x will be equal to the derivative of 1/2 times x, and the derivative of x to the first power is just equal to its coefficient. And so the derivative is equal to 1/2. All right, and so f prime of x is 1/2, so we'll plug that into our definite integral. So we'll have 1/2 squared and then times dx. Okay, and so now we have a definite integral that represents the area of the surface of revolution in this problem. And so now all we have to do to find that area is solve this definite integral. And so let's simplify. We can start by pulling this 1/2 to the outside, and note that 2 times 1/2 is 1, so they actually end up canceling each other out. So we'll have that this is equal to pi times the integral from 0 to 6 of x times the square root of 1 plus 1/2 squared. And 1/2 squared is 1/4, and then we'll multiply by dx. Okay, and so then we can simplify further. 1 plus 1/4 would be 5/4, and so this is equal to pi times the integral from 0 to 6 of x times the square root of 5/4 times dx. Now the square root of 5/4 is just a constant, so we can pull that to the outside of the integral as well. And so if I clean up my work here, this will be equal to the square root of 5 divided by 4 times pi times the integral from 0 to 6 of x times dx. And now we have a pretty simple definite integral that we know how to solve. And so let's integrate. This will be equal to the square root of 5/4 times pi times the integral of x, which if we use the power rule of integration, we'll add 1 to the exponent and then divide by that new exponent. So we'll have x squared divided by 2, and that will be evaluated from 0 to 6. Okay, and so now if I clean up my work again, we can evaluate this expression at 6 and then subtract the evaluation at 0. And so this will be equal to the square root of 5/4 times pi times 6 squared divided by 2 minus 0 squared divided by 2. Now I could have done this earlier, but I want to simplify this square root a little bit. We can take the square root of the numerator and the denominator. So what we'll have is that this is equal to the square root of 5 divided by the square root of 4. And we know that the square root of 4 is 2. So I'll just rewrite that as 2. So we'll have 2 times pi, and then that's multiplied by 6 squared, which is 36, divided by 2. And then we are subtracting 0, since 0 squared is 0, and 0 divided by 2 is still 0. Okay, and so then this is equal to pi times the square root of 5 divided by 2 times 36 divided by 2, which is 18. All right, and then 18 divided by 2 is 9, and so this is equal to 9 pi times the square root of 5. And that will be the area of our surface of revolution formed by this line revolved around the x-axis. And if you want an approximate value, 9 pi times the square root of 5 is approximately equal to 63.22. So that's what the actual value would be if you're interested in seeing that, but either of these answers would be acceptable. So here's our next example. We want to find the area of the surface formed by revolving the graph of y equals 2 times the square root of x on the interval 4 to 9 about the x-axis. Okay, and so let's start by drawing a graph of y equals 2 times the square root of x. I'll begin by drawing the y-axis, and then I'll draw the x-axis, and then I'll label them. So this is the y, and that's the x. And then the graph of 2 times the square root of x will be very similar to how the square root of x would look. It might just be compressed a little bit, but we're not worried about drawing a perfect graph here. So let's just say that 2 times the square root of x looks something like that. Okay, remember that the square root function just looks like half of a parabola that would be pointing in the positive x direction. And so this is y equals 2 times the square root of x. And now we're looking at a specific portion of this function, or this curve, from x equals 4 to x equals 9. And so if we say that this is x equals 4 and this is x equals 9, then a specific part of this curve that we're looking at here will be from this point at x equals 4 to this point at x equals 9. And so the curve between those 2 points is the curve that we will be revolving around the x-axis. And so once again, I'm going to draw an arrow around the x-axis so we remember what axis we are revolving around. And so if we did revolve that curve from x equals 4 to x equals 9 around the x-axis, then the surface of revolution would look something like this. All right, so we'd have these circles that together would make up that surface. And so if I connect the circles at the bottom, and you could start to see that surface that is formed. And so if we want to calculate the area of that surface, we will use the formula that the area of the surface is equal to 2 pi times the integral from a to b, which are 2 values of x, of the radius in terms of x, times the square root of 1 plus f prime of x squared times dx. Okay, and so let's start setting up this definite integral. We know that a and b are going to be the x values of the endpoints of our curve, and so that would be x equals 4 and x equals 9. So we'll have that this is equal to 2 pi times the integral from 4 to 9. And now we need to determine what our radius will be in terms of x. And so since we're revolving around the x-axis, the radius will be equal to the distance between that axis, the axis of revolution, and our curve. And that's just going to be equal to this function, y equals 2 times the square root of x. Right? This distance right here is the radius, r of x, and that's just going to be 2 times the square root of x. So r of x is equal to 2 times the square root of x, and so we can plug that into our definite integral and have 2 times the square root of x times the square root of 1 plus f prime of x squared. And so once again, that is the derivative of f of x, which is the line that our curve comes from that we were revolving around the x-axis. And so that function will be this line right here, 2 times the square root of x. And so just like we did for the previous problem, we can let f of x equal y, and so that means that f of x will equal 2 times the square root of x. And then to find f prime of x, we will take the derivative of this function. And so first let's rewrite it. We can rewrite f of x to be equal to 2 times x to the 1/2 power, and then we'll be able to more easily see how we're going to take the derivative of that function by using the power rule for derivatives. We will multiply that exponent down and then subtract 1 from that exponent. So f prime of x will be equal to 2 times 1/2 times x to the negative 1/2 power, right? 1/2 minus 1 is negative 1/2. And so we can simplify. 2 times 1/2 is just equal to 1, so these will cancel out. And so we're just left with x to the negative 1/2 power, which can be rewritten to be equal to 1 divided by x to the 1/2 power, right? We can move that to the denominator to make that exponent positive, and then we can rewrite x to the 1/2 power to be the square root of x, and so that is equal to 1 divided by the square root of x. And so f prime of x is 1 divided by the square root of x, and so we can plug that into our formula here. And so within this square root, we have 1 plus f prime of x squared, which will be 1 divided by the square root of x squared, and then multiplied by dx. All right, and so if I clean up my work here, we now have a definite integral that represents the area of the surface formed by revolving this curve around the x-axis. And so now all we have to do to find that area is solve this definite integral. And so I'll start by pulling this 2 to the outside. So 2 times 2 pi will be 4 pi. So this is equal to 4 pi times the integral from 4 to 9 of the square root of x times the square root of 1 plus 1 divided by the square root of x squared. Now 1 squared is 1, and the square root of x squared will just be x, because this square and that square root will cancel each other out. So we just have 1 divided by x, and then times dx. Now we can actually simplify this further, because we are actually allowed to multiply this x through this square root, since it is also underneath a square root. And so if we do that, we'll have that this is equal to 4 pi times the integral from 4 to 9 of the square root of x times 1, which is x, plus x times 1 divided by x, which will be x divided by x, which is just equal to 1. So I'll rewrite that to be 1. So we'll have x plus 1, and then multiply by dx. Okay, and so if I clean up my work here, our integral is now in its simplest form, but in order to integrate it, we are going to need to use u-substitution because we have a composite function, right? This composite function has an outside function of the square root and an inside function of x plus 1. And so if we set u equal to that inside function, we should be able to use u-substitution here, right? Because remember, whatever we set u equal to, its derivative also needs to be within this integral. And the derivative of x is just 1, which is a constant, and so we're totally fine here. We can use u-substitution with no problems. So we'll set u equal to x plus 1, so we'll have u equals x plus 1, and then we'll take the derivative, so du dx is equal to 1, right? The derivative of x to the power of 1 is just equal to its coefficient, which is 1 in this case, and then the derivative of 1 is 0 because 1 is a constant, and the derivative of all constants is 0. So then we can multiply both sides by dx, and so we'll have that du is equal to dx. And now we can rewrite this integral in terms of u. So this will be equal to 4 pi times the integral from 4 to 9 of the square root of u times du. Right, so we replaced x plus 1 with u because that's what we set it equal to, and we replaced dx with du because that's what we found that that was equal to. And so now we can rewrite the square root of u to be u to the 1/2 power, and then we can integrate that using the power rule of integration. And so we'll add 1 to that exponent and then divide by that new exponent, and so this will be equal to 4 pi times u to the 3/2 power, since 1/2 plus 1 is 3/2, divided by 3/2, and that is evaluated from 4 to 9. All right, but then dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so instead of dividing by 3/2, we will multiply by 2/3, which makes this equal to 4 pi times 2/3 times u to the 3/2 power, evaluated from 4 to 9. And now what we can do is pull this 2/3 to the outside and then replace u with what we set it equal to, x plus 1. And so if we do that, this will be equal to 4 pi times 2/3 times x plus 1 to the 3/2 power, evaluated from 4 to 9. Okay, so remember to replace u with what you set it equal to before you evaluate it at these bounds, since these bounds are values of x and not values of u. All right, so I'll clean up my work again. Now we can evaluate this expression at 9 and subtract the evaluation at 4. Okay, so this will be equal to 4 pi times 2/3, and so that will be equal to 8 pi divided by 3, and that will be multiplied by 9 plus 1 to the power of 3/2 minus 4 plus 1 to the power of 3/2. Okay, and so that will simplify to be equal to 8 pi divided by 3 times 10 to the 3/2 power minus 5 to the 3/2 power. And so this right here would be the final answer. It would be the area of our surface of revolution, but it's not a very nice answer and isn't very satisfying. So if you were to plug all of this into your calculator, you would find that the approximate value of the area of our surface is 171.2582, and then some more decimals. And so while this is the exact value of the area, this approximation will also work. Okay, so these both represent the area of our surface of revolution formed by revolving this curve around the x-axis. Let's look at one more example problem for this video. All right, so here's our final example. We want to find the area of the surface formed by revolving the graph of y equals the cubed root of x plus 2 for 1 less than or equal to x less than or equal to 8 about the y-axis. All right, and so let's start by drawing a graph of y equals the cubed root of x plus 2. And so here's our y-axis, and then here's our x-axis, and I'll label them. So this is the y, and this is the x. And then this is a little bit of a tricky function to graph, but the general shape of the cubed root of x is this shape right here, except it needs to be shifted up 2 units in the y direction. That's what this plus 2 tells us. And so I'll back it up a little bit here. If this is y equals 2, then our curve will look something like this. All right, it's not perfect, but that's going to be y equals the cubed root of x plus 2. And then we are interested in the specific portion of this curve from x equals 1 to x equals 8. And so, if this is x equals 1 and this is x equals 8, then we are looking at the curve from this point to this point. And so this curve right here is the curve that we are going to be revolving around the y-axis. And so I'll label that as well. We are revolving around the y-axis this time. And so if we revolve that line around that axis, we will form a surface of revolution. And so if we want to calculate the area of that surface, we will need our area formula that says that the area of the surface is equal to 2 pi times the integral from a to b of the radius in terms of x times the square root of 1 plus f prime of x squared times dx. All right, and so in this case, our bounds of integration, or the two values of x for the endpoints of our curve, are 1 and 8. So we can start by writing that this is equal to 2 pi times the integral from 1 to 8. And then our radius in terms of x, the radius is equal to the distance from our axis of revolution, which is the y-axis, to our curve. And that distance, r of x, is just equal to x, right? Wherever we are along this curve, the distance from that point to this y-axis is whatever value of x you are at along the x-axis. And so r of x is equal to x. All right, and so then back to our definite integral, we will have x times the square root of 1 plus f prime of x squared, which is the derivative of the function where our curve comes from. And so that function is y equals the cubed root of x plus 2. So if we let f of x equal y, then f of x will equal the cubed root of x plus 2. Now the cubed root of x can be rewritten to be x to the 1/3 power, so I'll have that. And now we can see how to take the derivative of that by using the power rule for derivatives. And so f prime of x will be equal to that exponent multiplied down. So we'll have 1/3 times x to the power of 1/3 minus 1. And that will be negative 2/3. Okay, and then the derivative of 2 is 0 because the derivative of all constants is 0. And so we have f prime of x is equal to 1/3 times x to the negative 2/3 power. All right, and so now normally I would move that negative exponent to the denominator so that it's positive, but it's actually going to be easier to work with that as a negative exponent, as you'll see in just a little bit. But first, let's plug in this derivative in for f prime of x in our square root for our definite integral. So we will have 1/3 times x to the negative 2/3 power squared and then times dx. All right, and so if I clean up my work here, we can simplify this integral a little bit by squaring this derivative. And so this will be equal to 2 pi times the integral from 1 to 8 of x times the square root of 1 plus 1/3 times x to the negative 2/3 power squared. Now 1/3 squared will be 1/9, so we will have 1/9, and then that's multiplied by x to the negative 2/3 power squared. And so all we have to do to square that is multiply these exponents, and so negative 2/3 times 2 will be negative 4/3. So we have x to the negative 4/3 power times dx. All right, and so now this is where things can get a little bit tricky because at this point, this integral seems to be in its simplest form. However, it's not very obvious how we are going to solve it. We know that we probably want to use u-substitution since we have a composite function. However, if we set u equal to that inside function, the derivative of that cannot also be found within our integral. And so u-substitution is not going to work for this integral in its current state. We need to manipulate it just a little bit so that we can use u-substitution. And so we're going to use a little trick here. What we can do is pull out a 1/9 times x to the negative 4/3 power out of each of these terms. Right, so here's what I mean. We could rewrite what's inside this square root to be the following. We'll have that this is equal to 2 pi times the integral from 1 to 8 of x times the square root of 1/9 times x to the negative 4/3 power times 9 times x to the positive 4/3 power, and then plus 1/9 times x to the negative 4/3 power. Right, so what I did there is I just rewrote this 1 to be this expression right here. And this is still equal to 1 because 1/9 times 9 is still equal to 1. And x to the negative 4/3 power times x to the positive 4/3 power is also still equal to 1. Because when you multiply these, the exponents are added together. And so negative 4/3 plus positive 4/3 is 0. And x to the power of 0 is equal to 1. So this is still equal to 1. So we really didn't change what's inside this square root. We just wrote it in a different way. And then we kept this second term exactly the same. But now we can pull out 1/9 times x to the negative 4/3 power out of each of these terms. And so if we do that, this will be equal to 2 pi times the integral from 1 to 8 of x times the square root of 1/9 times x to the negative 4/3 power times 9 times x to the 4/3 power plus 1 times dx. All right, so if we pull 1/9 times x to the negative 4/3 power out of this first term, we're just left with 9 times x to the 4/3 power right here. And if we pull it out of this second term, well, that's everything that was there, and so we were just left with 1. Okay, and so if I clean up my work here, we can simplify this by taking the square root of each of these factors, right? Since they're being multiplied by each other, we can take the square root of each of them individually and separate them. And so here's what that looks like. This will be equal to 2 pi times the integral from 1 to 8 of x times the square root of 1/9 times x to the negative 4/3 power times the square root of 9 times x to the 4/3 power plus 1 times dx. Okay, and so now that we split this up, what we can do is actually take the square root of both of these factors in this square root, right? We could rewrite this to be both of those terms to the 1/2 power, and so the square root of 1/9 is 1/3, and then if we multiply these exponents, we can take the square root of x to the negative 4/3 power. And so what we'll have is that this is equal to 2 pi times the integral from 1 to 8 of x times 1/3 times x to the negative 4/3 power times 1/2 and 4 divided by 2 is 2, so this will change to be negative 2/3. We will have the power of negative 2/3. All right, and that's still multiplied by the square root of 9x to the 4/3 power plus 1 times dx. Okay, and so now what we can do is pull this 1/3 to the outside and then multiply x to the first power times x to the negative 2/3 power, and those will combine to be x to the positive 1/3 power. And I'm going to tell you in a second why that is important. But first, this will be equal to 2 pi divided by 3 times the integral from 1 to 8 of x to the 1/3 power times the square root of 9x to the 4/3 power plus 1 times dx. All right, and so let me clean up my work again. The reason we went through all of that manipulation is that now we can use u-substitution. If we set u equal to this function inside the square root, the derivative of x to the 4/3 power will be on the outside of the integral. Right? If we take the derivative using the power rule, we end up subtracting 1 from this exponent, and 4/3 minus 1 is 1/3, and so that matches up with x to the 1/3 power right here. And so u-substitution is now going to work. That is why we went through all of that seemingly extra work. It was actually necessary in order to solve this integral. And so I'll set u equal to 9x to the 4/3 power plus 1. And then if we take the derivative of that, we'll have du dx is equal to 9 times 4/3 times x to the 1/3 power, right? We multiply the exponent down, so we have 9 times 4/3, and then subtract 1 from the exponent, and 4/3 minus 1, like we discussed, is 1/3. And then the derivative of 1 is just 0. Okay? And so if we simplify, du dx is equal to 9 times 4, which is 36, divided by 3, which is 12. So we have 12 times x to the 1/3 power. Now, if we solve for du by multiplying both sides by dx, then we will have that du is equal to 12 times x to the 1/3 power times dx. Now, whatever du is equal to, we need to be able to find that within our integral. Now, I see x to the 1/3 power in dx right here and right here, but I do not see 12, and so I'm going to divide both sides of this equation by 12, and so if I do that, we will have that du divided by 12 is equal to x to the 1/3 power times dx. And now we have a term of du that is equal to something in terms of x that we can replace in our integral. And so now we can rewrite this integral in terms of u. So we'll have that this is equal to 2 pi divided by 3 times the integral from 1 to 8 of the square root of u times du divided by 12. Right, we replaced 9 times x to the 4/3 power plus 1 with u, because that's what we set it equal to, and we replaced x to the 1/3 power times dx with du divided by 12, because that's what we set that equal to. All right, and so if we pull this 1/12 to the outside of the integral, we'll have that this is equal to 2 pi divided by 3 times 12, which is 36, times the integral from 1 to 8 times the square root of u times du. All right, and so if I clean up my work here, we can simplify this. 2 pi divided by 36 is just going to be pi divided by 18, and then we can rewrite the square root of u to be u to the 1/2 power, and then we will be able to see how we're going to use the power rule of integration. So this is equal to pi divided by 18 times the integral from 1 to 8 of u to the 1/2 power times du. And now we can integrate. We'll add 1 to our exponent and divide by that new exponent. So this is equal to pi divided by 18 times u to the 3/2 power divided by 3/2 evaluated from 1 to 8. Okay? And then dividing by 3/2 is the same as multiplying by 2/3. And so this will be equal to pi divided by 18 times 2/3 times u to the 3/2 power evaluated from 1 to 8. And then we can pull out this 2/3 and then rewrite u to be what it was equal to in terms of x. And so if I clean up my work again, we can rewrite this to be equal to pi divided by 18 times 2/3 times 9x to the 4/3 power plus 1 to the 3/2 power evaluated from 1 to 8. Okay, so we just replaced u back with what we set it equal to, so now everything is back in terms of x, and we can evaluate at 8 and subtract the evaluation at 1. And so we no longer need any of this u-substitution work, so I'm going to erase that. And now we can work towards getting our final answer for the area. So this will be equal to 2 pi divided by 18 times 3, which is 54, times 9 times 8 to the 4/3 power plus 1 to the 3/2 power minus 9 times 1 to the 4/3 power plus 1 to the 3/2 power. All right, so this will be equal to pi divided by 27, right? We can reduce 2 pi and 54 by a factor of 2, and then multiply that by 9 times the cubed root of 8 to the 4th power, right? So we could rewrite this to be 8 to the 1/3 power to the power of 4. If we multiply those exponents, we still have the 4/3 power, and the cubed root of 8 is equal to 2. So really we have 2 to the power of 4, and 2 to the power of 4 is 16. So I'll rewrite that. So we have 9 times 16 plus 1 to the 3/2 power minus 9 times 1 plus 1, since 1 to the 4/3 power is 1, and 9 times 1 is 9, plus 1 is 10. And so right here, we have 10 to the 3/2 power. All right, so I'll clean up my work one more time, and this will be equal to pi divided by 27 times 9 times 16, which is 144, plus 1 is 145. So we have 145 to the 3/2 power minus 10 to the 3/2 power, and that is our final answer. That is its simplest form. We can't really simplify it any further, but it's not a very nice answer, and so while you could say that this is the area of our surface, we should also give an approximate value since this is so ugly. And so the approximate value, if you were to plug all this into your calculator, will be 199.48, and then some more decimals. Okay, so both of these are acceptable answers. Both of them are going to be the area of the surface formed by revolving this curve around the y-axis. All right, and so with that, that was the last example for this video. If you have any questions, feel free to leave those in the comments below. But if you don't have any questions, this is all I had for now. So I will see you next time.